All right, so I'm going to give this a shot. While this is not the first lecture I've recorded, I obviously had to record a ton of lectures last spring. This will be the first lecture I've ever recorded for Physics 213, which is what you're in. But first, kind of a little bit about how the class is going to proceed. Basically, I'm going to post a lecture, 2 lectures a week. I will have sort of open office hours, and they're going to run from 5:35 to running this to 6:50, and that's going to be both Tuesday and Thursday, and that's in Jabara 128. Now, if you come, so if you come, let me know. I can only have, I think, like 23 students in the class, and I just can't be over capacity. I'm assuming that most are not going to come. I mean, maybe 10, maybe 15, that's fine. But I can't have you all show up. So make sure that you let me know, number one. Number two, if you do, please, you need to wear a mask. Everyone has to wear a mask. Going on, they say it's about your safety, and it is, but to be honest, it's also about my safety, because if I were to go to the hospital, I would lose money by teaching this class, and I don't want to do that. So, yeah, it's also about me, too. So, yeah, wear a mask, basically. All right. So there's that. There's that. All your tests are going to be online. I've never done that before. That is completely new to me. But that's what's going to happen. All of your tests are going to be online. All of your homework is going to be online, although you will have, I think, roughly 3 to 4 written homeworks where basically I give you problems outside of the book and you solve them, and I'm either going to have you turn them in person if you want, or in the uh, my box in the physics office downstairs, or you can email it to me. I haven't really decided. A lot of this I'm going to kind of have to make up as we go along, because I have to anticipate that things are going to change this semester. So just kind of play it by ear. If for any reason I have to go into quarantine, then my office hours are completely going to move on Zoom. So there's that. But for now, moving on in our lecture. All right, so your physics book starts off with basically kind of dimensional analysis, units, and measurement. It's kind of review. Some people skip it, but I feel like it's kind of good for you to have a little bit of review, so we'll start with there. So conversions and measurements. Physics uses the Système International, the SI system, better known as the metric system, where you have your basic units defined there. Length is a meter, mass is a kilogram. Mass and weight are two different things, remember. Time is in seconds, generally. You can do other ones, but seconds is the most common. Temperatures in Kelvin, although Celsius and Kelvin have the same change, so they're just off by a factor of 273. Amount of substance is a mole, volume is liter, and so forth and so forth. Those are the most common ones we're going to use in this class. There are others, but I kind of put the most common ones on there. A kilogram is still currently measured, I believe, off of a platinum iridium alloy, or maybe they just switched over. Um, they were in the process of that. I need to look that up, because they were in the process of switching that over to be based off of a unit. So and then finally, there are derived units. Derived units are essentially, meters a second for speed, or kilograms per second for mass flow rate, and so forth. So most of you should know how to do this stuff already. So I will do some couple example problems, because you're going to need to convert units. Not terribly often, but enough that it's pretty important that you know how to do it. So I'll start with the highest point in this state, Mount Sunflower. It's 1,231.4 meters above sea level. We'll express this in feet. There's a picture of Mount Sunflower. It's not really a mountain. It's simply just a flat plain in a prairie. That's my wife right there. In addition to worshiping bears and trees, she also apparently worships prairies. So, fun. All right, let's start off here. Basically, you take your first number that you have, 1231.4, and immediately write that over 1. And why do I do that? Well, there's a lot of reasons. Number one, it's going to help me solve the problem. Number two, 1234, 1.4 meters divided by 1 is 1231.4 meters. Then I use my conversion factor. There are some in the book, you can look them up, but the main conversion factor for this one is going to be 3.28 feet occurs for every meter. I put my 3.28 feet up top and my meter on the bottom. I do that because the meter, this is basically one long line, kind of like when you did stoichiometry in chemistry. And basically your meters cancel out, and that leaves you with only a unit of feet. And when I take 1231.4 and multiply by 3.28, and I didn't type in the right number in my calculator, so let's try this one more time. 3.28, there, oh, didn't do that again. 1231.4 times 3.28, got it finally, and that is 4,039 roughly. So the highest point in Kansas is 4,039 feet above sea level. Just to give you kind of a scale, Wichita's like 13 to 1,400 depending on where you're at. Campus is closer to 1,400, I believe, and it's also closer to 1,400 near the Air Force Base. And there's a little high point right up there. So, anywho, so 4,039 feet. All right. Next up is a problem with derived units. Well, we have a kangaroo here. This is a gray kangaroo. I took this picture when I was in Australia 2 summers ago. But more importantly, in Australia, they express everything in kilometers an hour, just like in Canada. And we do miles an hour, so let's convert it. All right, and my pen is acting up. Okay, let's go here. Pen, wonder why I did that. Okay. All right, so we take my 64 kilometers, and I put that over 1 hour because that's exactly what it means. It means you travel 64 kilometers for every hour. We want to get rid of kilometers, and we want to go to miles. There are 1.61 kilometers for every 1 mile. That means kilometers cancels out, and I get miles over an hour, which is exactly what I want to have. And so I simply take 64 divided by 1.61, and I get 39.8 miles an hour. 39.8. And it really is miles over an hour and not mph. At least that's a more proper unit because it kind of shows you that you have a miles for every hour. Whereas the P is, well, it's more of a, we'll call it a physics slang for lack of better terms. So, but anyways, so this is how you do it with derived units. The end game is all the same. You want to get your proper units of what you want in the end of, say, X over Y. And we'll do a different problem here. This is my tent, and whenever you go buy a tent, depending on where you're at, it's all on different crazy units. But my tent floor specs are 7'4" by 4'7". We're going to express this in square meters. Because I take I've been to every province in Canada, and whenever I go there, I've bought a few things up there, and they do everything in square meters, whereas we do it in feet here, and it's kind of confusing. But I've had to do this, basically, is what it boils down to. All right, so 7'4" by 4'7". Different ways we can do this. First, I want to take my 7'4" inches, and if I multiply that by, 7 times 12 is going to be 84 plus the 4 inches. That's actually 88 inches. Because that's another thing that we kind of do in America. We do 7'4", which isn't even in the same units. It's putting 2 different units together. But that's just kind of how it goes. And then that's pretty narrow. It's 4'7" in the other direction. And 4 times 12 is 48, plus the 7 is going to be 55 inches. All right, so a conversion factor, there are 2.54 centimeters, and that's going to equal 1 inch. Okay, and then, of course, you should know that there are 100 centimeters in a meter. So What I'm going to do is I want to get this in meters by meters, and then I can, multiply it out. So that'll be what I do. All right, so let's start off with 88 inches. We have 88 inches over 1, and I want to get rid of inches. So I say, okay, for every 1 inch, there are 2.54 centimeters. Inches goes away. Then we get centimeters. But I want meters. We already discussed this. So, okay, for every 1 meter, there are 100 centimeters. Centimeters cancels. That means your only unit you have left is meters. So when I multiply this out, I will get an answer in meters. And I get 2.23 meters. If I can find my... Where am I? Oh, there I am. So 2.23 meters. I think that's what I said. Let's hope. Okay, and then we'll do the same thing for my narrow width of 55 inches. And there are 2.54 centimeters in an inch. Inches cancels. And then when I'm, whoopsie, one more step. And then I need to convert that into meters. And so I take my 55, I multiply that by 2.54, and then I divide that by 100, and I get 1.3, we'll go 1.40. Word or note here is that significant figures, I usually try to stay within one significant figure of my starting values. So here's 3, and that was 2. It's not really important like it is in chemistry so much in physics. I mean, it is important, but I'm not as picky about it. I'm more concerned about how you can solve the problem. I would get annoyed if you were to write 1.397564328. Yeah, that would be really annoying. So you should kind of do the same. Anyway, so we want it in square meters. Just like in square footage, you would multiply these two values together. And so when I multiply that by 2.23, I get 3.11. So the square meters, the area of my 10 is 3.11 square meters. So, okay, trig review. Couple things. We will always be dealing with right triangles in physics. Just to recall, H is your hypotenuse, and that's always on the longest side of the triangle. H naught is going to be your opposite side, for the opposite. And while I didn't label this, we'll just call this HA, and that will stand for our adjacent side. So, things you need to remember. Well, you have sine. In physics, we usually call our angles theta. So you have sine of theta. And sine, of course, is going to be opposite over your hypotenuse. So this would be H naught over H. Your, erase this here, cosine, if you remember, is adjacent over hypotenuse. So that'll be H, I think I called it A over H. And then we have tangent, which is your opposite over adjacent. So that'll be HO over HA. These are really the only three we're going to be working with. Yes, there's cosecant and secant and cotangent and things like that, but we really just stick with the three main ones, sine, cosine, and tangent. Most of the time, what we're going to be doing is expressing it as a vector. So basically using my sine here and coming down here, I see that H naught over H is equal to sine theta. So if I multiply both sides by H, I would get H sine theta is equal to H naught. Likewise for cosine, it would be H cosine theta is equal to H A. This is how we're mostly going to express our vectors. It's always going to be your hypotenuse, then you're going to have some sort of trig function, and then you're going to have angle. We will not get to vector projection until really chapter 4, more so, at least with forces. But this is literally how you're going to do it every time. You just take hypotenuse times the angle, and the trig function times the angle, and then that gives you your opposite side or adjacent side depending on the situation. So that's just really all the trig you need to know. However, it's going to be a little bit harder than that because you have to actually apply it. All right, so we'll do an example problem. We have a dung beetle is at the North Platte River, about half a mile from the base of Scottsbluff National Monument. That's this little doohickey right here. The beetle is looking up at the peak of around 15.8 degrees above the horizontal. How high does the bluff rise above the river in feet? So I'll draw a very, very basic picture. Here's my beetle. I'll just put a B for beetle. Well, let's give him 6 legs. There. Perfect. Beautiful beetle. All right, and so it's looking up at 15.8 degrees. And here is my bluff, is this side. So we're looking for this side, which I will call Y. I could call it anything I want. I just called it Y because that's usually what we're going to be using, especially when we start getting into later chapters. So what I know is that this side, it says he's half a mile from the base. So that's 1/2 of 5,280 feet. So this side is going to be 2640. All right, so we have an angle. We're looking for the opposite, but we have the adjacent. So when we have the adjacent and the opposite, we're looking at tangent. And so, okay, well that means the tangent of 15.8 degrees is going to be, in this case, Y over 2640. Normally, I would always convert feet to meters. Just ask for it in feet, so I'm going to keep it in feet. And so when I multiply it by 2640, we have 2640 feet tangent of 15.8 degrees is equal to Y. This is the exact same structure that I pointed out in the previous slide. We have, in this case it's not a hypotenuse, but we have the adjacent trig function angle is equal to whatever vector we're trying to produce. All right, so so when you calculate this, make sure that you are in degrees. I think in this class, even when I factor in physics 214, physics 2, I don't think we ever switch to radians. So just make sure you're always going to be in degrees. Everything should be fine. All right, so it says 747 feet. All right, so basically put this side, this right here is 747 feet above the floodplain, which is about accurate what the actual value is. And you can take a little trail, and there's actually a really cool tunnel that you can go through this bluff in the middle of it, and it's kind of like their city park, which I kind of found cool. So, anywho, and then if I wanted to get the total height, I would just take 747 plus 3,900. So, fun. All right, moving on to scalars and vectors. You've been thinking, oh, well, you've been using those words a lot. What do they mean? Or maybe you know what they mean, and that's great. But, well, here's why. We have scalars and we have vectors. Scalars describe size or magnitude. Scalars do not have what's called, well, what we call direction. So a scalar is kind of like your mass. Let's say I weigh 200 kilograms. That's a little higher than what I weigh, but, or rather that my mass is 200 kilograms. It's not in any direction. It's just 200 kilograms. A scalar would be like, oh, I don't know, 30 miles. Doesn't say 30 miles north, east, south, west. It just says 30 miles. Vector would give it direction. So it would be 30 miles to the north. That'll get you roughly to Newton. 30 miles to the south, get you roughly to Wellington, and then so forth. So a vector actually has to have magnitude and direction, whereas a scalar is just a number. This matters a lot when you start doing like computational physics, and so that's kind of where it comes from. We'll list a little bit there. The length of a vector is usually proportional to its magnitude. So let's say let's draw me a little triangle here. This side was 5, then this side would be 4, and then this side would be 3. Okay, I didn't do a great job there, but basically my 5 is at least longer than my 4 and my 3, and so when you draw your vectors, you want to draw them roughly proportional to each other so that you can take a look at your picture and say, okay, who's bigger, who's smaller, what's the bigger force here, what's the bigger distance, and et cetera, et cetera, et cetera. Vectors are written in the book as bold letters. Sometimes you'll see vectors written as, I don't know, it'll be like A, and then sometimes you'll see a hat. But in your book, it just simply makes them bold. And that's how you kind of know it's a vector. It really only matters in this chapter and maybe chapter 4 and 5. Other than that, as long as you know the definition of a vector, it shouldn't affect you too much. But just know that vectors have magnitude and direction. So now, moving on to my next little picture here, we have vector addition and subtraction. Vectors that are parallel can simply be added. For example, if we'll say we have 5 miles going that way, and then after we do 5 miles, we say, screw that crap. I need to go 5 more miles this way. I didn't go far enough. We would add those two vectors together to create a larger vector, and it would be, and I didn't draw my arrow proportionate, 10 miles. So vectors that are parallel can be simply added. This also applies to anti-parallel, meaning if this were, let's redo this real fast, 5 miles in the opposite direction, I would still add them together, but I would get nothing. Be a scalar, because there'd be no direction. You went one direction, turned around and said, crap, I forgot X, Y, and Z. I've got to go back and get it. And then you go back and get it, so you'd have 0. Vectors aren't really always going to be parallel. That would make life easy. No. Vectors are often perpendicular, which means they simply cannot be just added together like I just did that. The resultant of the vectors must be found. And there's kind of a different way of writing it. So here is my triangle. We have my R, we have my A, we have my B. As I said, when you have vectors, you put little hats on them. Or you can be bold. I put hats because I didn't really have a way of doing it bold, at least at the time. And so when I write this in vector format, I would say R, the R vector, is simply equal to the sum of the A and B vector. Note that this is not R equals A plus B. It is not that. Okay? It's not equal to that. It's that R hat, R vector, A vector, B vector. When you add those two vectors together, you get the resultant. That's what it means by that. Vectors that are not perpendicular must be found using some sort of graphical technique, and we will do an example of that here in a moment. All right, let us do that example. Oh, wait, I gotta do this first. Whoopsie. All right, vector addition and subtraction. When a vector is multiplied by -1, the magnitude remains the same. Magnitude, remember, is size. But the vector reverses direction. So a good way of thinking this, just kind of in something that we're kind of more used to, Newton is 30 miles, a positive 30 miles away if we count up being positive. If I multiply that by -1, that takes me going to the south, so that would take me to Wellington. The size, the magnitude, how far you drive is going to be the same. You're going to drive 30 miles in either direction, but the direction is what changes. Now, so one more interesting facet of it from previous slide, I said that A plus B in vector format was equal to R. Well, you can also say that A is equal to R minus B, or that b is equal to r minus a. Remember, it's not truly equal to those numbers. It's only when we factor in those vectors that they're equal like that. And likewise, we can say a is equal to r plus a negative b, and that b is equal to r plus a negative a. More on that when I do an example here in a second. It'll make a little bit more sense. So let's do that. All right, components of a vector. Yeah, I keep promising these examples, and they're getting there, I promise. Last thing, components of a vector. The components of a vector are perpendicular and add together to get the original vector. So this side is our x. X means horizontal, right? This is that side is our y. Y means vertical. And so when I take ax vector plus ay vector, I get the resultant side r. We're only ever going to deal with two dimensions in this class, so we're only ever going to find a horizontal and a vertical vector. And that's literally how you're going to approach every problem. Find your horizontal component, find your vertical component, then figure out your overall value. All right, so the distance from the ground to the top of the CN Tower of Toronto is around 3,186.3. And I'm literally saying it from, like, say, this point right here. And so if I were to draw this out, this would be 3186.3 meters. The angle from where I'm looking at it is going to be around 10 degrees. And then we need to find our vertical component, AY, and our horizontal component, AX. That's the CN Tower. It's in Toronto. This is, I think, Toronto Islands Park. There's actually a body of water between this park and the CN Tower because you have to take a ferry over on Lake Ontario to get there, which is kind of cool. But anywho, so I need to find out my horizontal and vertical components based off of this, and we should get roughly accurate readings into how high the tower is. A couple different ways I can do it. Remember, I told you it was always going to be hypotenuse, then trig function, and then angle. Well, we'll write it in that form for now. Let's start with AY, my opposite side. All right, so let's take my hypotenuse, which will be 3186.3. If I want to find AY, notice that AY is on the opposite side of 10 degrees. Opposite. So opposite means sine. So I take 3186.3 times the sine of 10, and that's going to be equal to AY. Just to kind of give you a little refresher, that's the same thing as saying sine of 10 degrees is equal to AY over 3186.3. That's where we have opposite over our hypotenuse. I'm generally just going to write it in this form pretty much from here on out. It's just because it's easier that way. So, all right. So what does that mean AY is going to be equal to? All right, so that gives me 3186.3 times the sine of 10 degrees. Looks like 553.3. And so that's the height of CN Tower. So over half a kilometer tall, which is kind of pretty intense. So then we'll do the same thing for my horizontal side. Erasing it to give myself a little bit of room. In hindsight, I probably should have given myself more room. So we take AX, and that's going to be equal to my hypotenuse, which is 3186.3 times the cosine of 10 degrees. And so we take 3186.3 times the cosine of 10, and that's going to give me 3138. So meters. Okay. Never forget units. I took off a half point each time I don't see units, particularly like on tests and homework and things. So, all right. So that gives me my horizontal and my vertical components. And indeed, from this point, I would be around 3 kilometers away. And remember, that's like 2.5 miles away. And then the height isn't in the miles, but it's still half a kilometer tall, which is pretty tall. So, anyway. Okay. Okay, additions by vectors of vectors by components. Basically, sometimes it's not as simple as going, 5 feet to the right, 10 feet up, something like that. Basically, you may go, going down here, let's say you go, I don't know, 45 degrees to the west of north, and then you go 15 degrees to the south of west. What are your x and y components there? So this is more common on the type of problems that we're going to be doing. And so you have to break it down into multiple components. So I'm going to label this leg here A, and I'm going to label this leg B. So basically you're going to go up A and then kind of a little bit down B to get to your final destination, which is right here. And so what you got to do is you got to find your x and y components of both of them. This right here, let's see if I can do this real nicely. Okay, I can't do this really nicely. Try this one more time. Okay, this is better. This right here is the first leg of your movement, and it needs to have its x and y components like the rest of them. Can get better at this. So this would be side AX since it's horizontal. And then this side right here is going to be AY. Then you're going to go down a certain amount. And you need to find this side, BX, and this little side right here, BY. And why do you need to do that? Because you need to find your every horizontal component that exists and every vertical component that exists. This will create a new triangle, dot, 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 which I will call C. And then this would be CY. And then this entire side is going to be CX. And so you're trying to sum up each of your individual components, meaning your CY is going to be your AY plus BY, and then your CX is going to be AX plus BX. So the AX is how far horizontally you went in the A run, and then the BX is how far horizontally you went in the B run, and then the same for the AY and the BY. Now, notice I did say add them, and this is actually going down. Well, that would need to be a negative, or you'd have to use a different type of angle, or there's a lot of different factors there. But for now, you're adding them. By saying adding, it could be addition or subtraction. That's really what it means. And so this is what we'll have to do from the next two problems, is find our x and our y components, and then put it all together in one big wonderful package. So, without further ado, we shall do that. Okay, so let's do an example problem with components. A local tourist at Devil's Golf Course in Death Valley wanders 30 degrees west of north for 400 meters, turns and then stumbles 300 meters at 25 degrees south of east. Determine the magnitude and direction of the resultant vector. This is Devil's Golf Course. It's a unique geological feature in the very lowest, actually I think it's at the very lowest point of Death Valley, which by the way reached 130 degrees yesterday. Highest temperatures recorded since I think 1913. Anywho, probably easy to get lost, especially if you get dehydrated, all that good stuff. Or bad in that case. Bad stuff. Bad stuff is what I meant to say. Alright, anyways, so the first step is to draw a happy little XY axis. So that's what I'm going to do. Little dots here. And I blew up this so I can make it a little bit easier to see. Erase this a little bit. Okay. And then this side is north, this side is east, this side is west, and this side is south. So it was 30 degrees to the west of north. So if I were to go directly north, I would go right along this line. But I don't want to do that. I want to go 30 degrees to the west of north. This is going to be my A vector. Then it says I'm going to go south of east. So I'm going to make a line, little dashed line, that is parallel to my x-axis. I know that I'm going to go 30 degrees to the south of east. And then I make a new triangle. Okay. And then this is going to be my B side. So, all right. So I need to find components. There's a little this is an angle right here, and then this is an angle here. This side right here is going to be BY. I'm starting with it because it is the clearly easiest to see. And by that, I'm going to have to move that. There we are. And then this side, I'm going to erase north because we already know that, is going to be my BX. All right, so it's harder to see here because it's kind of superimposed by each other, but let me make a different color here and maybe try to outline this. There we go. So we have this triangle right here, which I highlighted in a different color here. And so what I want to do is find the opposite side of that triangle. So what I'm looking at here is going to be my AX, YAX, because it's the horizontal, even though it's the opposite side of my angle. And then I'm going to put this over here, put my AY. And that's this little green area going up and down. So, I've got all of my vectors drawn appropriately. I need to figure out what vector is going to do what. Find AX, AY, and then so forth. So I'm going to do that right now. Let's start with AX to go in alphabetical order. AX is on the opposite side of this angle. Opposite means sine. And so it's going to be A sine of theta, or it's going to be 400 meters sine of 30 degrees. And so when I put that into my calculator, 400 sine of 30, I get 200. But I'm going to do something crazy. I'm going to put a negative 200. Why did I do that? Why? Oh, because it's going to the left. Well, where did that come in? Well, I'm going to tell you. So we generally say that up is positive and that right is positive. Any other direction will be negative. So since it's to the left, I make it a negative 200. All right, well, what about AY, you ask? Well, I will tell you. All right, so that's going to be A cosine theta because it's to the adjacent side of my angle right there. So then I take 400 meters and I cosine my 30 degrees. And kind of sounds like a alone, cosine alone. All right. And I get 346, I think. Yeah, 346. And that's going to be positive since it's going up. All right, let's do the same with my B's. BX is going to be B cosine theta. Why? Because BX is to the adjacent side of that angle, which is this inner angle right here. And so that's going to be 300 cosine of 25. Let me make sure it's 25. It is. And that's going to be 272. And that's a positive because it's going to the right. Then BY. That's going to be the sine, so it's the opposite. So it's going to be 300 sine of 25. And that gives me 127. But not just any 127. Oh no. Negative 127. Why is it negative? Well, because notice that we went to the south of east. So since there's south right there in it, that means we're going to be going down or toward the origin. East means we're going to be positive. So while we're going in the positive horizontal direction, we're going in the negative vertical direction because we're coming back towards the origin. So that's why I made it negative. Now, from the last slide, I told you we have to find CX and CY. And so I take AX plus BX. And so AX was my negative 200. Plus BX is 272. And CX is going to be 72. All right, let's do CY. It's going to be AY and BY. And so that's going to be 346 minus 127. So 346 minus 127 is going to be 219. And that's still positive, meaning we still went away from the origin in the positive y direction. Okay, so I've got my CX and CY. Well, why did I do all that? Because ultimately what we're trying to do is create a new triangle. Going up here, we wanted to create a triangle that looked like this. When you add up all your components together, you get a triangle that looks like this, even though you had multiple movements to get there. That's what we're doing. And so, based off of my CX and CY, usually what I do is I just draw it from what my numbers are. CX is 72, so I start with that one. I go, okay. Actually, I need to go a little bit down here. 72. All right, 72 meters. And then you have to draw a head-to-tail vector. So the next vector is 219. So at the end of that vector, I draw one bigger because it's a larger number, 219 meters. And then I take from where I started and draw a dashed line to where I finished. And so from where I started, that's the angle I'm going to need to find right there. All right. So I first need to find C, the actual absolute distance that you traveled. If it corresponds to the original picture, we're basically we're finding it like somewhere around here. All right, so how do I do that? Well, Pythagorean theorem. Remember, C squared is equal to A squared plus B squared. All right, or C is equal to the root of A squared plus B squared. I'm normally going to write it like this. So let's do that. C is equal to the root of, what was that value? Let's see here, 72 and 219. So 72 meters squared plus 219 meters squared. And then plugging that into my calculator because I hadn't done this ahead of time. And don't forget to root it. You get 231, we'll round it. So. All right, so my C value, we've gone a total of 231 meters. Yeah, we may have gone 400 and then 300. So like we've actually traveled, 700 meters, but we've really only gone 231 meters. Well, how's that possible? Well, actually, I use the example of a tourist because when people get lost, they tend to go in circles if they don't know where they're going. And so you end up not really far from where you started, even though you may have hiked like 25 miles and died of like dehydration or something. So it's kind of interesting, at least in that respect, how people tend to go in circles. And some people talk in circles, like I'm doing right now, talking in circles. So in here, 231, and then I need to get the angle. You can do it different ways. I always use tangent. So the tangent of theta is going to be my opposite side. So the opposite is going to be 219 to the angle. I don't need units, yay, because units cancel, yay. And so remember, to solve this, you take the inverse tangent of both sides. So the inverse tangent um, of both sides. So basically, you're taking the inverse tangent of the tangent of theta, more or less. And when you do that, you get we're gonna go 72 degrees. Let's erase that. All right, what is that 72 degrees? Well, that just tells me the degrees. Well, okay, so this is the positive x direction. So I can say 72 degrees from the positive x-axis or direction. That's one way of putting it. Notice that I could also express it as from the negative x direction. Whoa, why would I do that? Sometimes they do that. It would actually be 102 degrees from the negative x direction. I don't think you have anything in your homework problem that does that, but I figure I should at least cover it. Because why? How did I get the 102? Remember 180? 180 degrees, doubled 360. So 180 minus 72. Totally split. It should have been 108. I know what you're thinking right there. 108. Where's the 102 coming from? That's because I apparently can't do math. So there's that. All right. So normally how I would usually express this would be to do north of west and things like that. And so in this case, it's 72 degrees. And so this would be directly north. This would be directly east. And so it's actually going to be to the north of east. So I would say it as 72 degrees north of east. So multiple different ways you can express it. I think your book will take all sorts of answers as long as it lines up in their little framework in terms of what Wiley accepts. I think I give you the first two turns to get it right. After that, I start taking off points because every once in a while it is like rounding and how you word things, and that's why they take off points. So, yeah. Anywho, do one more problem. This one has stars on it because usually when I lecture in person, the stars means if I have time. Since I'm actually just doing the lecture remotely, I suppose I do have time. So yes, we have time. Let's do this one. You are wandering around the Great Sand Dunes National Park. It's in Colorado. You walk east of north for 2 kilometers at 45 degrees. You then turn right at 15 degrees south of east, and you walk another 5 kilometers. Find the results at magnitude of the hike. This one doesn't say direction, just says magnitude. So keep that in mind. All right, let's draw a little XY axis here. Here's north and do, and then some do. Okay, we're dude. All right, we're dudes. All right, you walk east to north for 2 kilometers at 45 degrees, so it's to the east of north. So it's not directly north, it's to the east of north. So I'm just going to do zoop. And then we'll say that's 45. It's close. One of the better times I've actually done that. That's east to north, right? We'll call that A. And then you turn right at 15 degrees south of east. So similar to the last one. This would be directly east, so it's parallel to my x-axis. And you want to go much... Oh, that's really bad. Ooh, let's try that again. Sorry, penmanship is not what it used to be these days. I got S's in grade school in writing. S's were C's. S minuses were D's. I got roll back grades. Okay. So, just one more time. Come on. That's better. Oh, that's much better. All right. And I made that bigger. Why? Because it's 5 kilometers as opposed to 2. Fun. All right, so this side's going to be my bx. This side's going to be my by. This side is going to be my ax, and this side, sorry, ay, and this side's going to be my ax. All right, so, and then this side's my inner angle, which I can't quite put in there. Same deal. We're going to, put in some numbers, see what happens. Start off with ax. All right, ax, same deal as last time, although it doesn't matter as much. More on that in a second. It's opposite the side of my angle, so we're going to be doing sine. And so it's going to be a, and my a vector was 2. So I'm going to take 2 sine 45 degrees. And so plugging that in to my handy dandy calculator gives me 1.41. I'm just going to go, we're going to do 1.41. It actually matters in this problem. All right, so 1.41 kilometers, and that's positive. And then we do the same for AY. When I said it didn't matter what angle I use, well, it's because it's 45. When you take the cosine of 45, you get the exact same number. If you remember from your trig classes, 45 was a 1 square root of 2, square root of 2 being the hypotenuse triangle. So, all right, so there's AX and AY, BX and BY. BX. All right, so BX is adjacent to the B, and so that's going to be 5 cosine, I think it was 15. I'm going to double check it. It is. So 5 times the cosine of 15. Cosine of 15 is really small, so it should be small. 4.83, or rather should be large. And that's going to be positive. And I just noticed these are all supposed to be kilometers. So if you noticed, good for you. Because I didn't notice till now. All right, so next up is BY. I'm going to take 5 sine of 15. This one will be rather small, 1.29. But not just any 1.29. Oh no. It is negative 1.29 kilometers. Why? Well, because it says to the south of east. You're actually heading south, back towards the origin. So that's why I make it negative. And so basically, this one's a little bit easier to draw it. Let's make it blue. So basically, we're creating a new triangle like so. Where this side's going to be your CY, and this side's going to be your CX. And then we're going to find this angle right here. So, changing back to my easier to see black color, and then we'll do CX and CY. Alright, so CX is AX plus BX, so it's going to be 1.41 plus 4.83. And so when I take 1.41 plus 4.83, I get 6.81. And then for CY, I'm going to take 1.41, subtract 1.29. So 1.41 minus 1.29. Should do that in my head, but I didn't. 0.12. So, I exaggerated this a bit, but what really happened when I redraw it down here is that we went 6.81 this way, kilometers, to the right, sorry. This way, that's not very descriptive. And a paltry 0.12 kilometers north. And so when we connect the two, as the crow flies, we need to find this side C, and we need to find this angle theta. So remember, C is equal to the root of the two. We Pythagorize the crap out of it. At least that's usually what I say. So I take 6.81 kilometers squared plus 0.12 kilometers squared. So let's do that. Square u plus 6.81 squared. Your squared to have 6 point, little bit larger, but nearly 6.81. Probably should choose a different example. I say that every year. I always forget to change it until I do it. So we really just traveled 6.81. It's actually 6.811, so it's slightly more. So pretty small. Just because that 0.12 is just too small to contribute. We don't need to know the angle, but if I were, I would just do the arctangent in order to figure out what my angle is. It'll be extremely small. In one respect, this is good because there are a few assumptions we're going to make when we get to chapter, I believe, 10 about pendulums and really small angles. And the fact that your hypotenuse is pretty much the size of one of the sides of your triangle. It's actually used a lot, I believe, in astronomy, if I remember correctly, but it's been a long time since I've studied that. So, anywho, that's it for Chapter 1. I hope to post Chapter 2 soon. If this one seems a little bit discombobulated, I've had to stop this a few times and then restart it when I made a mistake, or I was interrupted. So, but luckily I know how to use OpenShot, so I can just put it all together like one big piece. But that's kind of why it looks a little bit different. So the next lecture should be better as I get better at this, but I'm using different software again because something else had to happen to change that, and so it's going to take me time to kind of get used to it. So if you have any questions, please email me. You don't, like I said, need to come to class really ever, but if you want to, that is fine. If you've got COVID reasons to stay home, I get it. If you still want to come in, I know a lot of students like in-person stuff, so that's kind of why I'm still having it, although I do not want to get sick. Well, actually, I don't really care about getting the flu or crap like that. I don't think I want this COVID, man. That's just, that'll screw me up 3 ways from Sunday, and I hear that's pretty rough, so. All right. I will post a lecture hopefully in the next few days. That was it.